of random integers.
Thanks, Alexei. I would like to start with expressing my sincerest gratitude to organizers for gathering us here. This is a brilliant, outstanding scientific event. I'm very impressed with the program, with the way we communicate with Kiev. Despite the small technical issues, everything works perfect. I hope Kiev can hear me well.
Yes.
This is also the first event organized by newly created mathematical center in Ukraine. So, as we can all see, this is a top-level event, and I hope and wish that all events in future will be maintained on the same top level. And of course, as a part of Ukrainian mathematical community, I'm always eager to help in any way with this. Okay, let's go. Let's do mathematics. So first, I will start with a disclaimer, short disclaimer. So my primary field is probability theory and stochastic processes. So I did my PhD and my habilitation in pure stochastic process. But actually, during my PhD studies, I encountered a very simple problem from multiplicative number theory, probabilistic multiplicative number theory. I will explain in a few minutes what kind of problem is it. And since then, this topic of distributional limit theorems for multiplicative arithmetic functions is never fading part of my research. Of course, as I mentioned that I'm a probabilist, so my talk will naturally be biased towards probability. In particular, I will use some vocabulary which is very common in probability, but might sound unusual for some, especially young students. But so please interrupt me and ask any type of question related to notation or notions from probability theory. But I will try to be as elementary as possible. Okay, so I mentioned that during my PhD studies I encountered some problem from number theory. So the problem can be formulated very easily. So let's start with some permutation of a finite set. So please give me some permutation, some numbers.
1, 2, 3, 4, 5.
Let's take something more interesting.
This is the end of the day.
Acceptable. Okay. 3, 4, 1, 2, 7, 6, 6 point, so 8, remains 3. Okay, so this is a permutation of a set of 8 integers, right? We can write it in cycle notation. So we form cycles. So we start with 1, 1 goes to 4, 4 goes to 2, 2 goes to 5, 5 goes to 7, 7 goes to 8, 8 goes to 3. Very good. So we see that our peaking random number resulted in a unique cycle, right, of length 8. Sorry, I forgot. Indeed, I forgot 6. Thank you. So then there are 2 cycles, one of length 7, raises 1, and one of length 1, which is 6. Okay, and why the cycle notation is important for us? Because if we denote this permutation by sigma, the order of the permutation sigma, which is defined as the smallest number such that sigma is an identity, can be defined as the least common multiple. So this is my notation for the least common multiple of a cycle length. So these are cycle lengths. Right, in our case, this is just 7. So in this example, this is LCM of 7 and 1, and this is. So now, where is the probability? So let's put some measure on the set of all permutations. Then sigma becomes a random element of a group of symmetry group of on n elements, and this quantity, order of sigma, becomes a random variable. And if you take a group of large size n, so this is our symmetric group, Right, so we are interested in behavior of this quantity, which now also depends on n, and sigma n is picked according to some measure. And the classical result called Erdős-Turan theorem tells us that if you put a uniform measure on Sn, so mu is a uniform on Sn, so this means that every particular sigma is taken with probability 1 over n factorial. So then I will write it in this way, so probability that logarithm of the order of sigma n minus 1/2 log n divided by square root of 3 over 2 log cube n, here probably square. So probability that this is smaller than x converges for every fixed x as n goes to infinity to a standard normal distribution. So this is e minus q over 2 dt. So for any fixed x. If you don't like this letter p, so this is the same as saying that and here we take indicator that this quantity, we put it here, so as n goes to infinity, this sum converges here. Right. Since everything is uniform, these are the same. So you see that this is actually a result on least common multiple of some random sample of integers. Right? Of course, if sigma is taken uniformly at random from Sn, the cycle lengths are not independent. This is a dependent sample, and this is a result about the least common multiple of random integers from a dependent sample. So this is Erdős and Turan law. Erdős-Turan law. 1939. Okay, so we generalize this result in some way, which I don't want to describe here. But what is important is when, during the study of this Erdős-Turan law and its generalization, I started to search what is known actually about least common multiple of random integers. And I was surprised that not much is actually known, even for independent integers. And that's the topic of my talk today. So I will discuss what is the asymptotic behavior of this kind of things, either LCM, or I will also discuss greatest common divisor, or more generally so-called multiplicative functions of random samples. I will introduce this notion later. And for this talk, in this talk, I will always assume that these are just independent random integers. What does it mean? I will also introduce in a moment on my slide. Okay, now let's take a look on the slides. So, what was actually known? This story has started almost 200 years ago with a result by Dilation, who proved that two random positive integers are coprime with probability 6 over pi squared. By the way, we already encountered this constant yesterday. This is the asymptotic density of what? Of square free numbers, right? Also 6 over pi squared. And Dilation used the following heuristic argument. We already encountered this kind of reasoning yesterday and today. So take some prime number p. So it divides a random integer with probability 1 over p. Right? So if p is 3, so we expect that random integer is divisible by 3 with probability 1 over 3.
Okay.
Something has happened there.
At them. Oh, then I don't make it worse. At them over.
Okay, now let's take two independent random integers, and they simultaneously are not divisible by p with this probability. So we expect that for different p, this probability should be, this event should be independent, and therefore we get this infinite sum. And here in this infinite sum, you might recognize an inverse of a zeta function. So this first equality is called Euler's product identity. Yeah? Euler's product or Euler's product formula.
Sorry to interrupt.
Yep.
I think the key is complaining that they stop seeing the slides. So when you try to see
It's kind of strange because I see in the screen. It's our screen.
So we're having some technical problems. If we could perhaps wait just a little bit.
Absolutely.
Yes, so we are sharing. By some reason they don't read it.
Okay, perfect. We solved the problems. Thank you.
Okay, very good. And meanwhile, I've written this general formula for Euler product, right, which relates product over prime numbers with the values of zeta function. Right? And this is a one-line proof, probably familiar to all of you. So we take this infinite product. So we write this as an infinite sum of geometric series, right? And then we realize that taking products over all prime numbers of this kind of sums gives us all possible products of these forms, right? And by the prime number theorem, what is it? How to call the theorem which states that every integer can be decomposed into
Fundamental theorem of arithmetic.
Fundamental theorem of arithmetic. Thank you. Right, so this gives us this formula, and this is by definition a zeta function of m. Right, so this heuristics explain how this 6 over pi square appears. Right? This is an inverse of a zeta function. So this result has been generalized by Cesaro to any finite number of positive random integers, and it's not surprisingly in view of this heuristic, the result is 1 over zeta function evaluated at m. Right, where m is a sample size. Very good. So, as a probabilist, so I would prefer to write this result in the following form. So, probability that greatest common divisor of m independent uniformly distributed in this set integers. So, the probability that they are coprime is 1 over zm in the limit as m goes to infinity. Actually, much more can be said. So let's replace here 1 by some fixed integer k, then the following holds true. And again, as a probabilist, I would write it in this way, which is called convergence in distribution. Right? So we already encountered convergence in distribution here. So this can be equivalently written as this guy converges in distribution to a standard normal law. Right? And in general, convergence in distribution, let me recall, means that expectation with respect to the probability measure of f of xn converges to the expectation of f of x, xn goes to infinity, for any f which is continuous and bounded. Continuous and bounded. And this is very useful definition because it works not only for random variables taking values on the real line, but also for random elements taking values in arbitrary topological space. This is the notion of continuity and boundedness. For the if xn and x takes values just on the real line, so this is equivalent, as I wrote while speaking about Euler-Turan law, that this function converges pointwise to this function for any t which is a continuity point of the limit. Right, so these are equivalent for me. And furthermore, if my xn takes values in set of integers, like in this example, this is equivalent to this for all k. As here you see that I wrote this limiting random variable in the following form, using some weird, at first glance, geometric random variables. Let's show how this infinite product pops up. First of all, why is it convergent at all? This is an infinite product. And so it's not clear at all why it's convergent, because at first glance, as for large p, it's not clear why this goes to 1, right? But it turned out that it actually converges. And converges, and the distribution of this series is exactly this. Let's check this claim. So, K from 1 to n. First of all, let's understand what is this. So this is a random variable. And we calculated distribution as follows. So minimum of independent random variables. So they're by definition independent. So this means that this random variable is larger than or equal than I. And there are m of them. So this, by definition, is probability that one of them is larger than I, and we raise it to power m. And by definition, this is 1 over this, right? And we actually proved a very natural fact that minimum of independent geometric random variables is again a geometric random variable with this parameter power n. Right? This notation for me means that these two guys have the same distribution. Right? So the same distribution function is the same probability mass function. Very good. So now let's work with this infinite product. So I will pass to the logarithm to transform product into the sum. And I take what is called Laplace transform of this logarithm of this. So this gives me expectation product over all primes. Here it's this is just the expectation of x m to the power minus lambda, right? This is by independence. So for different primes, my geometric random variables are independent, right? So expectation of the product of independent random variables is a product of their expectations. So this is a product of this. And here I write expectation of minus lambda right? I know what is this, right? I have exact distribution, precise distribution for this. And so I write it as a product here I write sum over j, and here I write. So this takes value j, this probability being difference of two consecutive numbers of this table. So times this. I don't have enough space. Let's calculate. So this is product. So this is sum minus lambda j gm 1 minus almost done. So this gives me just what, lambda plus m j and this gives me 1 minus m. And this is just a geometric sum, so this is 1 over 1 minus m plus j. And we recognize using Euler's identity. It was here. We recognize using Euler's identity that this is just zeta function at lambda plus m over zeta function at m. And we can rewrite it as follows, right? Right, this can be written as minus lambda log. And this is a proof. This is a proof that this random variable x infinity m has the following distribution. By the way, so this is the only place where I encountered in practice this kind of distribution in probability theory, even though it's very natural. It's probably the simplest discrete distribution you can imagine, probably except geometric one, right? When you think of a convergence series, right? Convergence series, first what you're thinking about is say 1 over k squared or 1 over k cube. And where did this distribution where did this distribution come from? This is an answer. So for example, this is a distribution of the greatest common divisor of an independent uniformly distributed random integers. Okay, these geometric random variables will play a crucial role in subsequent talks, so please keep in mind this definition. So important things. So this is a bivariate array of random variables. They are mutually independent, both in J and P, and each has a geometric law with this parameter 1 over T. P is a prime number. So indices are P from set of prime numbers, and J is 1 to up to M. Okay. So this was the story about the greatest common divisor. So what about the least common multiple that I have started with? So again, the first result is quite old, almost 150 years ago. So it was proved by Cesaro that if you take two independent random integers, raise it to the power, take the least common multiple, raise it to the power r, take expectation. So then asymptotically this behaves as written here. Again, some constant, right, times n to the power 2r. So basically this says that least common multiple itself behaves like a constant times n squared. So from this, using the method of moments, we can actually write it in this way. So these results tell us that expectation is the least common multiple of U1 and U2, and divided by n squared to the power r converges to this quantity. So here I use this asymptotic, and the first asymptotic is also interesting because we actually know this result already. Right? So if we divide not by n squared but by product of the arguments, so raise it to the power r, this will converge to this is not surprising at all, because what is written here is just 1 over the greatest common divisor. So 1 and u2. And we already know that this quantity converges to 1 over x infinity m. Right? So this Cesare's result is actually not surprising at all for two random variables because of this very neat relation between LCM and GCD for two arguments. Product of LCM and GCD gives us just the product of arguments. Surprisingly, more than 100, almost 130 years have passed before a result for 3 uniform random numbers have been proved. This was done in the paper by Fernandez and Fernandez. And they proved that if you take 3 independent random integers, so the moments of this quantity behave again as n cubed, right, to the power r is the same as here, times some constant. So they calculated this constant explicitly, but didn't give any hint what this constant is, where did it come from. This result has been improved several years later by Hilberding and Todd. By the way, this is also Raschel Todd, but this is not the same Raschel Todd as on Marina's Swazovskaya talk. It's a different Raschel Todd. And they generalized this result from 3 uniform integers to arbitrary number of random integers and calculated this constant in a closed form. If you accept that this is a closed form, right, as a following product. Again, few years later, so this result has been proved by completely analytic techniques from number theory. Later, so we have been able to reprove this result and give a very good characterization of this limiting constants. So here you see the result. So first of all, if you want to get rid of this product of independent uniform random variables, you just need to replace this n by the product of u1, u2, and so un. So let me write it here. Divided by the product, converges in distribution to what is called y infinity m, and y infinity m is again an infinite product over prime numbers, random product. And here we have very interesting power. Again, these geometric random variables pop up, independent, right, from the previous slide, exactly these random variables. And the prime p is raised to this power. Again, it's not clear at all why this infinite series converges, say, almost surely. And the key observation here is that this sum is either 0 or 1 for all but finitely many values of primes p. And whenever this sum of positive integers is 0 or 1, this means that the maximum is the same as sum, right? And this, which means that this power for all but finitely many values of prime p is just 0, which means that almost surely this product is, consists only of finitely many terms. Okay, very good. Now I want to explain how do these geometric random variables pop up. So far it's not clear at all where do they come from. And here is what I call a baby fact. A baby fact because it can be proved just in few lines, but it's a very actually quite deep result. By lambda pi, I denote, let me write it here. By lambda pi of n, I denote the power of prime p, in the composition of n, in the prime decomposition of n. Right, so I take a uniformly distributed random variable, and lambda pi of un are just powers of prime in the composition of this random integer picked uniformly at random from this set. And the appearance of geometric random variables come from this fact. Take an infinite vector of lambda pi indexed by prime numbers, and this vector converges in distribution as n goes to infinity to this vector of independent geometric variables. And furthermore, we have a joint convergence of these powers of prime and un itself normalized by n. And in the limit, so it's more or less clear that this converges to uniform on 0, 1 distribution. And what is important is that in the limit, components are independent. So this convergence, convergence of infinite vectors is just in the product topology, which means that this is a convergence of any finite projections. Let's prove this result. Actually, proof, as I promised, is just a few lines long. So I'll present a proof not for any finite collection, but just for two different primes. So let's take two different primes p and q. Let's fix some x between 0 and 1, and let's try to calculate this probability. So this probability that un is over n is smaller than x. We expect this to converge to x. Probability that un is divisible by p to the power cp, and simultaneously u is divisible by q to the power cq, right? Since p and q are different primes, this is the same as divisibility by the product. And since everything is uniform, this can be calculated explicitly in this way. Right? And as n goes to infinity, this converges just to this product. And this is a product of independent uniform coming from this x, and two independent geometrics coming from this and from this terms. Very good. So we proved this baby fact. And now I want to show you how to prove using this baby fact this convergence, and this convergence, or more precisely, yeah, this convergence. Right. So this on this slide I want to present three most basic facts from probability theory, which are very useful, and probably all of you know them, but still I want to recall them. So first is called Buraczewski and K lemma, and says that if you have a sequence of events, right, such that the probability decreases sufficiently fast, in this sense, the series converges, then events that there are infinitely many events in the sequence En occur has probability 0. And if, in addition, En are independent, then from divergence of this series, we conclude that probability that infinitely many occurs is 1. Right? Actually, I will need only the first part, or the easier part, but keep in mind that there is also a reverse of Buraczewski and K lemma, but it requires independence. And by the way, it's also true that events can be pairless independent. So this assumption can be lifted. Okay, the second lemma is sometimes called convergence together lemma. So what does it tell us? So we want to prove that psi m converges to some limit, say eta. So how do we do this? We introduce some truncations, sequence of truncations, psi t of m, which converges to some limit for every fixed truncation level t. So think of psi tn as a truncation of psi n. Then, as this threshold t capital goes to infinity, eta t converge to some limit. And if these truncations approximate our psi n in this sense, so then psi n converges to eta. This is an extremely useful result for proving distributional convergence. And finally, the next result is called continuous mapping theorem. It doesn't require any proof, so it's almost obvious from the definition that if we have a sequence of variables which converges in distribution, and we have a function f, deterministic non-random function f, which converges, satisfying this property, this means that the limit falls into the set of discontinuities of a function f with probability 0. Then from this convergence, we can deduce this convergence. Right? This is just merely a definition of reconvergence, yet very useful fact. Very good. So here is a proof how to deduce a limit for the greatest common divisor. So the first line is just definition of lambda pi, right? So instead of un, I put this product. Instead of um, I put this product. The next line is just a definition of the greatest common divisor, right? If you have prime decompositions, so the greatest common divisor is just this product. We must take minimum over this lambda pi for every prime p. Right? And since every uniformly distributed random variable is smaller than n, actually this is a finite product over primes not larger than n. And now I want to apply my convergence together lemma. So I introduce a truncation. So I fix some large parameter t capital and write this product as two products. Now, from the baby fact, I know that this quantities converges to geometric random variables. And since my product is finite, this is a continuous function of these lambdas. And therefore, by the continuous mapping theorem, this converges here. So it's not that difficult to show that in double limit as here, right? This product converges to 1. It's an easy exercise for you, the first exercise for this lecture. And now, finally, we must send t to infinity to get this one, but this is easy, right? If you send t to infinity, this is finite product converges to an infinite product. And we already know that this is an almost surely finite random variable, which we denote at x infinity. So basically, modulo this convergence, this double limit. So this is a complete proof of the convergence of the greatest common divisor of u1 and so on un. So a small remark, which will be useful later, is that this minimum is actually non-zero just for finitely many values of prime numbers. Right? This event. And this explains why this infinite product converges. Also. Very good. For LCM, for the least common multiple. So again, we do the same. And moreover, I will prove an easier result. I mentioned without this product of uniform random variables, but instead of n to the power m, I put just a product of this uniform random variables. Okay, so least common for the greatest common divisor, here it was minimum, and for the least common multiple, here is a maximum. It's also a trivial observation from arithmetics, right? And here we have a product, which means that we add this lambda pi's, right? We take a product. So this is just, yes, we again introduce a truncation, some at level t, and distribute this into two parts. Again, this, by the continuous mapping theorem, converges here, and this in the double limit gives us 0. Again, this is the second exercise for you to show that this in the double limit converges to 1. And as t goes to infinity, this converges to the following product. And I already mentioned why is it finite, because this sum is larger or equal than 2 for infinitely many values of p with probability 0, which means that almost surely it is either 0 or 1 for all but finitely many p. And whenever this sum is 0 or 1, this power is 0. Right? Which means that almost surely this infinite product contains just a finite number of terms. Okay, very good. So this was a proof for the simplest arithmetic functions, greatest common divisor and the least common multiple. But this approach is quite general and works for almost all arithmetic or multiplicative arithmetic functions you can imagine. So basically, Heuristics says that whenever you have a function of independent uniform random variables, so it can be approximated for large n by the same function f applied to this random numbers. And it is easier to deal with these random numbers because these geometric variables are independent. I will now give you an example, so which shows that how this approximation can be used to prove a deep result from the from number theory. So this heuristics helped to prove such things as Hardy-Ramanujan central limit theorem, Erdős-Kars central limit theorem, and these generalizations called Kubilius theorems with convergence to infinitely divisible laws. And I would like to mention here a very deep result by Richard Aratia. Unfortunately, I don't have time to prove this. This is a long 50-page long paper. But what does these results tell us? So what do we know? We know that two, 3 is the subprimes, number 5, and so on, converges in distribution to this array of geometric random variables, G2, G, my notation G2, G3, G5, and so on. But this is a weak convergence. Weakest possible type of convergence. In particular, these random variables can live in a different probability spaces. Right? This is just convergence of distributions. And Aratia's result tells us that it's possible to couple these sequences. To couple means to construct them on a single probability space in such a way that they are closed in a very strong sense. What does this tell us? This tells us that in order to transform this random number with geometric random variables into a uniform number, asymptotically we just need two switches, right? We just need to change by 1 powers of some two, at most 2 primes, right, on average. Which means that, roughly speaking, these two vectors can be coupled such that they differ just at 2 places on average. And this is a very strong coupling, right? Not only that this converges here, but the whole array converges with a high speed, relatively high speed. Let me show how this result can be used to prove, say, Erdős-Kars theorem. So Erdős-Kars theorem, in the simplest form, tells us that if we take the number of distinct prime factors of an integer n, if we denote by omega of n the number of distinct prime factors of n, so then we have this distributional convergence. So W, number of distinct prime divisors of un, centered by log n, normalized by square root of log n, converges to the standard normal law. Why is it so? Function W can be written just as a sum of indicators, right? We just count the number of distinct prime factors, and prime p is included into the prime decomposition of un whenever this lambda pi is larger than 1, right, by definition. So by Aratia coupling, if we replace these lambdas by our geometric random variables, this gives us a bounded sequence asymptotically, and then probabilists would say that the distribution of this difference is tight. Right? Yeah?
Should you go to the previous page?
Yes.
I wanted to ask you, is there any interesting, notable example of this minority of functions where this approximation doesn't work?
Doesn't work. I will say a few words why when this approximation doesn't work in 2 slides. Okay, so let's first consider the case when it works. So again, this approximation tells us that this random variable can be approximated by this random variable plus something tight, something which is bounded in probability in this sense. But this is just a sum of independent random variables, because for different primes, these indicators are independent. And central limit theorem is just for free. You get it for free. You just need to calculate expectation of this guy and variance of this guy. So here is a calculation for variance. For expectation, it's even simpler. So since they're independent, variance of a sum is the sum of variances. Variance of indicator is just probability of this event times probability of a complement. So this times this. Sum of 1 over pi squared is just bounded, right? And so we just use that sum over all primes smaller than n, 1 over prime is log n. So variance is for the log n. Expectation is easier, you just don't have this at all. It's again log n plus something bound. And that's all. Let's give you a very, how much lines? 5 lines long proof of the Erdős-Kass theorem, at least the simplest form of Erdős-Kass theorem.
Excuse me.
Yes.
This proof allows you to estimate the speed of convergence in Erdős-Kass theorem?
Yes.
Something they didn't have?
To be honest, I don't know whether the original proof contains some speed of convergence result, but this definitely gives a speed of convergence.
Some estimates, but I don't remember if they were at that time. For some people in number theory, it matters. Okay.
Yeah, but definitely this method gives speed of convergence.
If you compare the original proof and the Arrhetius proof, is Arrhetius itself a long proof?
This result, as I said, so it's a long paper dedicated solely to the proof of this fact.
So, objectively speaking, Arrhetius is deeper and longer.
Yes.
Erdős-Kass is application.
Yes.
Okay.
Yes. And now, going back to your question, so when this wonderful coupling doesn't work, so generally speaking, it works in all situations when we deal with just 1, 2, or some finite number of these uniform random variables. But whenever there are infinitely many of them, the cumulative error caused by these approximations for different uniform causes troubles. So here is the result. I don't want to go into details. It's again a result, a recent result. So what is different here? We take not a sample of a fixed size m of n, but sample of size m, but a sample of a size which depends on this n, right? So we have 2 regimes. In both regimes, we have this kind of central limit theorem. Again, there is a phase transition at square root of n. You see that variances are different. And both these results are incomparable to the result for when we replace this uniformly distributed random variables with this product of independent random variables. So you see that the difference, the variance is different in all these cases, which means that approximation of this guy by this guy doesn't work anymore. And they differ, so this log LCM and this are different just by the fact that here we will have lambdas here, not the geometric random variables. So this is to the best of my knowledge, the only example when this approximation fails, so it doesn't give a correct result. And the reason, morally speaking, is that we have too many terms which we have approximated, right? Not just a fixed number of terms that we approximated, but infinitely many in the limit of them. Okay, how much time do I have? When do we start? Did we start?
Yeah, well, it's more like the question of how much interruption we had, and I didn't in that time.
Okay, so as much as they wish.
In the good tradition of the conferences.
I understand that probably we're already tired, so I will try to finish in 10 or 15 minutes.
Yes, about 10, 15.
Okay, so the results that I have so far gave you. So there, in these results, we dealt with independent uniform random variables, right? And use this baby effect with convergence to geometrics. But actually, more can be said. And now I'm going to explain how to generalize this result. So first of all, note that saying that we work with m independent uniformly distributed random variables is the same as saying that we just take a uniformly at random a point from m-dimensional discrete cube. For example, for m equal 2 from this lattice. Very recently, so less than 2 years ago, I encountered a work again by Raschel and a different co-author, where they studied the following model. So they take a parabola, x times y smaller than n is a large parameter, and take integers which lie below this parabola in the positive quadrant. Right? And they work with, again, with greatest common divisor, or least common multiple, of a random integer picked from this finite set, which I denoted h capital n of 2. More generally, we can increase the dimension, work in m-dimensional discrete lattice, right? And take the set h and m to be the sublevel of this, I don't know how to call this, so multidimensional version of parabola, right? Just take a product of coordinates, assume it's smaller than n. So this is a finite set for every fixed n, and so we can take a point uniformly at random from hn of n. And Heyman and Todd proved, just in dimension 2, that again greatest common divisor converges to the same limit as for the square. So they didn't give any explanation of this fact. Again, this was just a pure computation. Now I want to explain you why this is true. So why we again get the same limit. So now what is important now is that these two coordinates are now dependent, right? The product is smaller than n, so they must be dependent. So, first of all, we generalize this result to any dimension. Again, the greatest common divisor converges to this x infinity m, the same object as on the first slide. And for the same is true for the least common multiple. Again, with the same limit. Okay. So this was just a particular example of a general phenomenon. So how to formulate this phenomenon? So let's take a sequence of finite non-empty subsets of the m-dimensional integer lattice. And since we assume it is finite, let's pick a point uniformly at random from this dn for any n, fixed n. Right? And let's ask ourselves the question, what are the conditions on the sequence of these domains such that this and this converges again to our limits x infinity and y infinity of m. And we have been able to find very general conditions for this to be true. The first type of condition is it's known from statistical literature under the name Van Hove condition. So just take a look on this condition. So what does it tell us? So we take dn is a large set of integers. So we slightly shift it, right, with a vector c. So take intersection with the original set, and we say that we require that asymptotically for every fixed c, we have the same proportion of points from Dn as the whole number of points in Dn in this shifted intersection. This is called Van Hove condition. Does anyone know this type of condition?
In quasi-crystals, they use it. It's,
very good, because so we will be able to prove solely under this condition convergence to the geometric laws. So here is the general result. So assume that this Van Hove condition holds. So this is a condition on a sequence of domains Dn. So V1, V2, and so on Vm is a vector picked uniformly at random from Dn. And solely under this Van Hove condition, we have convergence of these multiplicities of primes to independent geometric random variables. Again, this is in the product topology, which means that we have convergence of any finite projections. So for the greatest common divisor and the least common multiple, we need additional condition, but which is not that restrictive. So this is condition which I called uniformity. So if we take a subset of integer lattice such that coordinate number I is divisible by some fixed integer a, so we denote it by that I of a. So we assume that a set Dn is more or less so uniformly distributed, right, on the lattice of Z in this form. What does it mean? This means that the ratio of the number of points such that coordinate number I is divisible by A and coordinate number J is divisible by B should be some constant over A times B. So for example, the number of points in Dn such that the first coordinate is divisible by 2, right, and the third coordinate is divisible by 3 should be approximately 1 over 6. And of course, for fixed A and B, this is an empty assumption, right? We always can find K, but it's important that we require this to be true for any A and B. I will give examples of domains, of very general domains satisfying this kind of condition. So this is called uniformity. And under this condition, we proved that the greatest common divisor and the least common multiple in this sense converges again to our limits x infinity and y infinity of m. Examples. So we have basically two conditions, the Van Hove condition and uniformity condition. The first family of examples is related to the dilations of dilations of a convex body. So let's fix some compact convex set in the positive quadrant. Let's assume that it has a non-empty interior, and let's take any sequence growing to infinity, to plus infinity. And define the sequence Dn in this way. So we take all integer points in this dilation with scale an of a set D. Right? For example, if you take D to be a quarter of a unit disk, so we recover another type of summation studied by Heyman and Todd, so spherical summation over this type of domains. So in this example, whatever the domain D is, assumptions 1 and 2 are satisfied. Both these assumptions are satisfied. And the second family of examples is related to this hyperbolic summation I introduced before. So the second family of example works as follows. So take a function of m arguments with the positive values, assume that it is non-decreasing in each coordinate. And let's assume that it diverges over every fixed coordinate. So let's introduce these boundary domains. So what are these? What is written here? I will draw a picture. So this is point 1, n, and this is point n, 1. So these sets D and I are just precisely these sets. This is dn1 and this is dn2. And these assumptions, assumption 3, tells us that the number of points on the boundary must be negligible in compared to the number of points in the interior, which is, of course, quite natural assumption. And if this is true, in the sense that the number of points inside the domain is asymptotically larger than the number of points on the boundary, then the sequence of domains defined as sublevel of a function f satisfies both Van Hove condition and uniformity condition. Right? And in particular, if you take f to be just a product of coordinates, we recover this hyperbolic summation by Heyman and Todd. Okay, I have probably 5 or 6 minutes, and now I want to go to the general multiplicative arithmetic functions. So far we have we dealt with just greatest common divisor and least common multiple. These are just examples of multivariate arithmetic multiplicative functions. So let me recall first what is a univariate multiplicative function. So for this talk, I will assume that my multiplicative functions take values in the positive real, so I can take logarithm, so there is no problem with taking logarithms of negative or complex numbers. I will assume that values are just positive. So this is the definition. Whenever k and n are coprime, f of k times n is the same as f of k times f of n. This is the definition of a multiplicative function. And examples are well known, so this Euler-Stattine function, Möbius function, and any number to the power omega of n is also a multiplicative function. Omega of n, we already encountered this function. This is just a number of distinct prime factors of n. Right? These are examples of multiplicative functions. Right? And what's important is that every multiplicative function is completely determined by the values on the power of primes. Right? By definition, if we substitute instead of x of n its prime decomposition, and using definition, we can write it as follows.
Sorry, Möbius doesn't take positive value, it takes negative as well, but you wanted it to have positive.
Which function?
Möbius.
Good observation, yes. I included this example and then decided that for simplicity of my talk to assume that it will take only positive values. But you're right, of course. In this framework, Möbius function doesn't work. But in general, so multiplicative function is defined as a complex valued, so it's not a problem. But okay, so, and I would like to mention a very important result called Erdős-Wintner's theorem, again from the same year as the Erdős-Turan law. So let f be a multiplicative function. So then a sequence of random variables converges in distribution as n goes to infinity, if and only if this 3 series converges. This is called Erdős-Wintner's theorem. And let me briefly explain where these 3 series come from. Again, this is actually a probabilistic result. So f of a uniformly distributed integer can be written in this way, just by definition of lambdas. And I know that without any assumptions, this converges to my geometric random variables with parameter p. And therefore, the only reasonable candidate for the limit of this function distribution is the same product with geometric variables here. Right? And now the question is, when does this series or product converges? So as I said, for simplicity of the talk, I assume that everything is positive, so I will take a logarithm. And the question is when this series converges. Right? I denote this function by f small. And the first thing that must be recalled is this one. This one. This result implies that Actually, we don't even need this result. This is 1 over p squared, and this is summable. So by Buraczewski, this is larger than 2 just for finitely many values of primes p. And therefore, this series converges almost surely if and only if this series converges almost surely, but over indicator that this jp is equal to or larger equal to 1. And this is a series comprised of independent random variables, and there is a criterion for convergence of this series called Kolmogorov's three-series theorem. And this is exactly, if you write down these three conditions, three series, you'll get this three series. So basically, the Erdős-Wintner theorem is a version of Kolmogorov's theorem, or a consequence of Kolmogorov's theorem for this in the theory of multiplicative functions. Okay, so few final words. I will formulate a result for multivariate multiplicative functions, a version of Erdős-Wintner theorem, and we'll then stop. So, first of all, the definition. What is a multivariate multiplicative function? So, we now take a function of m integer arguments, and it's called multiplicative if this equation holds whenever product of all k is coprime with product of all n's. Right? And this is a condition on which we require multiplicativity. Examples. So, first of all, if you take usual univariate multiplicative function of GCD or LCM, these two functions are multivariate multiplicative. The second example, so I like it most. So take this group, just a product of finite abelian groups, and denote by C of N1 and Nr, these are just these indices, the total number either of a cyclic subgroups or the total number of subgroups. Then both these functions are multivariate multiplicative. And many further examples can be found in a survey by Guy Raschel. Okay, and here is the final result for today. So take a multivariate multiplicative function f. Define the function f of I in this way. So all arguments are equal to 1 except argument with index I. This is x. And let's assume that this 2 series converges for every fixed I. And assume that we have a sequence of domains, d of n, right, which satisfy the Van Hove condition and the uniformity condition which I introduced. Then there is a version of a Erdős-Wintner theorem, which states that these values of this multivariate multiplicative function applied to this uniformly distributed vector converges in distribution to a finite limit. For this limit to be finite, it's necessary and sufficient that these 2 series converges. Just a few words why there are 2 series here and 3 series here. So this result is necessary sufficient conditional for conditional convergence of this series. So the series might converge almost surely conditionally or almost surely absolutely. And these 3 series are necessary and sufficient, finiteness of these 3 series are necessary and sufficient for conditional convergence of this theorem. If we forget about this and put absolute value here, this will be a necessary and sufficient condition for the absolute convergence of this series. So for absolute convergence, we just need these 2 series. And in our theorem, we deal precisely with convergence of absolute convergence of this product or absolute convergence of the series obtained by a logarithmic transformation. That's why we require just these 2 series to be convergent. Okay, that's all that I wanted to say. There's a list of papers on which my talk is based, so if you're interested, I encourage you to take a look or ask me. Thank you for your attention.